Welcome to Wireless Future. I'm Emil Björnsson, and as always, I'm here with Erik Larsson. How are you today?
Oh, hi Emil. Very good. How are you?
I'm great, and today we have a guest, and that is Jakob Hoydis, who is a principal research scientist at NVIDIA, and you might also know that he was the founding chair of the IEEE ComSoc Emerging Technology Initiative on machine learning, and I believe he's one of the early visionary voices in terms of using machine learning in the communication area, and he's also been heading a research department at Nokia Bell Labs, so you might have seen him in a number of different situations before. But recently, he has joined NVIDIA and developed a GPU-accelerated open source link-level simulator for next-generation communication systems called Sionna. So that is the intention. We'll talk about that. So, Jakob, welcome. How are you?
Yeah, hi, I'm great. Hi, Erik. Hi, Emil. It's great to be here. I'm a big fan of your podcast and very happy that you have invited me. So
yeah, it's great to have you here. And I was really excited when I heard about this new system simulator or link level simulator. So really would like to understand more what it can be used for. So I think we will kick this off by just asking you, what is a link level simulation?
Yeah. So one typically distinguishes between link level and system level simulations. And link level simulations evaluate physical layer performance in the most detailed manner, I would say. And that means that one simulates the actual transmission and reception of information bits over a specific channel. And that involves also all of the necessary signal processing blocks, such as channel coding, modulation, synchronization, channel estimation, MIMO detection, and so on. So in other words, link-level simulations are important to validate the performance of signal processing algorithms, see if they behave well, and ultimately, if you come up with a new algorithm, you want to see that it leads to gains in an end-to-end scenario. And the typical metrics one is interested here are bit error rate or block error rate. And importantly, a link-level simulator does not require any information from higher layers, for example, the scheduler.
I see. So then you mentioned the system simulators as well, and I guess I happened to say that when I meant link before. So what is the purpose of those ones then?
Yeah, so system simulations are then used to evaluate performance of large networks, and typical metrics here would be the CDF of the uplink or downlink throughput, so over the entire cell. But as this is computationally very demanding, to simulate such large networks, one resorts to so-called physical layer abstraction. And that means that rather than simulating the actual transmission of bits as what is done for link-level simulation, one only computes SNIR values for each link, from which then block error rates are typically obtained through lookup tables. And what's important is that system-level simulators need to account for higher-level components such as power control, link adaptation, scheduling, hybrid ARQ, traffic models, and so on.
So, I mean, is it fair to say that a link-level simulator is a way of developing and parameterizing this abstraction that system-level simulators then later on rely on?
Yes, to some extent, I would say yes. But as far as I know, so these physical layer abstractions, they are even, I would say, simulated in much more simplified settings. So typically, you compute block error rates over an AWGN channel, and then ultimately you compute an SINR and then just assume, okay, this is the operating point on an AWGN channel that I'm currently looking at, and then I take this value.
Right. So now in the context of Sionna, I just learned that it's not Sionna, it's Sionna. Is that right?
Yes, that's right. That's Irish.
Irish, yeah. Wow. So in the context of Sionna, what are the link level performance metrics that you guys work with? I mean, some folks look at like capacity bounds, for example, and the capacity bound translates into like effective SINRs and so forth, and others look at bit error rate uncoded, bit error rate with coding, block error rate, and so forth. So what metrics does this system support?
So I mean, typically we look at coded bit error rate and block error rate, because that's what matters most when you develop an algorithm. But you could also compute SINR values after a linear detector and then take it and plug it into a compute capacity. But typically, when we do these link level simulations, we really care about, do we observe gains in coded bit error rate?
Yeah, of course. I mean, coded bit error rate or block error or packet error rate is typically what matters eventually, right? But then sometimes uncoded bit error rate can be a good enough proxy for that, and sometimes capacity or SINR expressions can be. But is my understanding correct then that Sionna actually delivers, like, I mean, you parameterize the link, you tell the system that this is the environment, this is the modulation, this is the decoder, or, which could be potentially, I don't know, it could be a classical signal processing algorithm, right? Or it could be some trained machine learning black box that does it for us. And Sionna will then give us for this set of parameters a block error rate as a function maybe of signal to noise ratio or transmit power and so forth. Is that how it works, or could you? No, not really.
No.
Okay, so
that's not. No, that's
so there is something more hidden
so
here.
No,
So
there's really no
more,
magic. There's no magic. Sionna is actually just, it provides you signal processing blocks. Like you have an encoder, you have a modulator, and in the encoder you feed in a vector of bits and get out a vector of coded bits, and then you put it in a modulator. It outputs you 16 QAM symbols, and then you might feed it into an OFDM modulator that outputs you a discrete waveform. And then you can say, hey, I would like now to send this waveform over a specific type of channel model. And then this channel model, you do Monte Carlo simulation that generates you random channel impulse responses. You compute the channel, the convolution of your input with this channel impulse response, get an output sequence, and then you do the processing until you finally end up with an estimate of the bits that were transmitted, and then you can compute whatever you want with it, like bit error rate, block error rate, and so on. I
see. So in that respect, Sionna is more like, I mean, in a way, it's like a classical link level simulator then, right? Where you have the blocks, you have your modulation, you have your coding, you have your channel model, you have your demodulator, channel estimation, decoding, whatever, and you get your bits. And then once you get your bits, you can obviously estimate your block error or bit error rate or anything else that you wish. But furthermore, I mean, from this entire chain, you could also get like an SINR value that could be used as a simple proxy for like capacity by plugging it into a Shannon formula or even with a finite block length correction factor and so forth. So, I mean, maybe a little
if we take a step back and we have been talking now about Sionna several times. So what is sort of the elevator pitch? What is Sionna, if someone asks you?
So it's a software library for GPU, so graphic processing unit accelerated link level simulations, which has native support for the integration of neural networks in the signal processing flow. And so we use Sionna for physical layer research at NVIDIA and have decided to make it available to the community as an open source project. Now, most of Sionna is written in Python using TensorFlow's Python API. So TensorFlow is a deep learning framework. And the idea behind it is really to make the daily work of researchers easier by allowing one to go as quickly as possible from a research idea to a simulated working prototype, if you want.
So, I mean, I understand that if you work with machine learning and particularly deep learning algorithms, then TensorFlow is one of the standard software packages to use. But for many components here, like modulation or even channel coding and so forth, I would think that just a classical implementation of the standard algorithms would be good enough or even better. So is there like a specific reason for why everything here is built upon TensorFlow? Or is it just that, I mean, there's TensorFlow underneath and it's used for the machine learning components, but for the classical stuff, just classical algorithms are implemented? Could you comment on that?
Okay, so first of all, there is no so what we implement are really textbook algorithms.
Yeah.
So whatever you have there, it's the same. So if you do it in, I don't know, if you modulate something using MATLAB or any other tool that's available there, you would get the same results. So there's no difference. But there for us there's three, I think, important components. The first one is that it's really open source, and I think our community is lacking an open source implementation of many standard algorithms. So for example, if you wouldn't really want to get a polar code implementation that you can use in your simulations, that's open source. There are some things available, but not everything you need. And so I think it's important so that we in our community have like an open source implementation of all of these things available. So I think that's very useful. The second thing is that as you said, as soon as you want to do something with machine learning, you have the problem that you need to interface your link level simulator now with a machine learning library. And then you start to generate with one tool, you start to generate data sets, and then you import it in your machine learning framework, do the training there, and then you kind of need to evaluate, hey, what happens if I replace a certain block with this trained model? What will happen there? And then you go back into your link level simulator to compute metrics. So things become very quickly complicated. And by integrating actually link level simulator with the deep learning framework, you get both. And then comes the thing is, Sionna is a differentiable link level simulator. And that's very important. So that means, so essentially we do differentiable programming, meaning you take any or almost any block you have available in Sionna, and you can get automatically the gradients of the outputs with respect to the input.
And that's
changes.
A cool thing. I mean, but how about channel coding, for example? Is it also differentiable if you put in like a, I don't know, LDPC code or something there, like multiplying with a parity check matrix doesn't sound like a very differentiable operation, right? When you have like zeros.
That's why I said almost every. That's why I said almost every component. Yeah. But so for example, the BP decoder is differentiable. So that's
yes.
fully different.
Yeah,
that's
the decoders, yes, I understand.
But
okay, yeah.
we can't yet. No. I think learn new codes. So make the parity check matrix differential would be great. But I think nobody has come up with a way of doing it.
Right, but at the same time, there isn't maybe a lot of point in trying to learn new codes either, because I mean coding is such a well investigated, and the codes that are out there are so good, right? At least for longer block lengths. I mean they are almost at the Shannon limit. So if I understood this well, I mean, it's like you build the entire simulation chain on the data structures and on the TensorFlow framework, but then you have, I mean, a number of components that just implement the classical algorithms that have nothing to do with machine learning or even with TensorFlow itself, but just coded into that, right?
Actually, Sionna there is no neural network in it. If you download the tool and use it,
it's
a
classic data types from TensorFlow, so that it integrates nicely in case you want to use a machine learning algorithm at some point in your like demodulator or somewhere. So that's yes, great.
Exactly.
So what are the like main competitors here in terms of like other tools that are available? I mean, for one thing, there's like in MATLAB, I think has some communications toolbox, and then there's this IT++ package, I'm sure you know, written in C++, that I don't think it does polar coding. Actually, I don't know with certainty, but I know for a fact it does LDPC coding because I wrote that module some 10, 15 years ago. What other like competing software packages are there? Or who's your like main competitor?
I like to avoid talking about competition because that's not how I really see it. So obviously you can do most of the, first of all, there is no differentiable link level simulator. So with respect, there is no competition. That's the reason why we developed Sionna. But for example, if you are really into channel coding, there's an awesome open source library called Effect. And I think they have state-of-the-art implementations from everything. So for this specific kind of, let's say, niche, I don't know if coding is not a niche, but for this specific research sub-community, that's a great tool. And I think then there are quite a few open source channel simulators. So just to generate channel impulse responses, there's this great tool NYU Sim, for example, that's really good. There's Quadriga, and so they do the channel simulation part. But then if you now want to use these channel impulse responses in a link level simulator, then you need to import it. And then you're back working with multiple tools at the same time.
Yeah, sure.
So in Sionna, you can also import these channel impulse responses if you want from other sources, but you don't need to.
Yeah, right. But Sionna like interface to any of the other? I mean, suppose you wanted to use this, say the name again for the open source toolbox for state-of-the-art algorithms in coding. Suppose you want to like import some particular, I don't know, exotic Polar code or LDPC code or something and just run it in Sionna. Could you interface then with those libraries, or are you more like a closed, well-defined simulation chain that, well, as long as you're within this like TensorFlow framework, then you can program anything, but you can't really interface too much with like other packages? Could you comment on that?
Ultimately, everything goes through Python. And so whatever you can interface to in Python, which is everything.
I mean, clearly you could always convert to data types, but you'd like the interface to be clean enough somehow so that,
So especially whenever you do this, you will lose this differentiability.
Yeah.
So whenever you interface with something else, you will lose this, but you can. And for example, so what I found the most important thing is actually that you can use, that you can import channel impulse responses from any source you want. So you can have measurements, you might have done some ray tracing experiments, or you want to use another channel simulator. You can just import it and then simulate transmissions over it in Sionna. I felt that is important. Now there is support, for example, you can import any parity check matrix if you want, and then use it. And there's a universal encoder and you can run any BP decoder on it. But now if you want to, for example, have a very specific implementation that you find in one open source library, you can't really use it. I mean,
not without some tweaking.
Yeah, exactly.
Yeah, I get that. I mean, you'd have to write some function that interfaces these libraries then. But I mean, it sounds to me that the main innovation here is really this differentiability, right? You can actually, I mean, well, in a way, back propagate to train like machine learning algorithms. That's a cool thing.
That's one thing. And there's the other thing, that's the GPU acceleration. And that makes things really, really, really fast. And then for me, that's a game changer, because you need to think about when you run, when you typically run Monte Carlo simulations, often you have a for loop where you say you iterate over 1 million iteration, then simulate things one by one. On the GPU, you do this in one shot. You say, generate me 1 million transmissions of a code block, and you get it instantaneously.
Yeah, so it's like the use of GPUs allows for massive parallelization of certain operations, right? I mean, as long as you stay within, I guess, the realm of like vector matrix multiplications and that sort of things, but perhaps even like in a channel decoder, I mean, you have the box plus operation, right, and the bleep propagation, for example. I suppose they could also be parallelized in a similar fashion. So
we mentioned channel, and particularly how you could potentially import something from other sources, but what kind of channels can you generate within Sionna? Because I'm thinking that this is one of the discussion items that always comes up when we are going to run simulations in my group. What selection of parameters should we have? And then in the end we select something simple and that has a name, and that's it.
Exactly. Yeah. So first of all, we have the basics, the basic textbook models: AWGN, Rayleigh fading with arbitrary correlation, if you want. And these models are great if you simulate a frequency flat fading channel and you don't care so much about mobility. And then we have implemented the full specification of 3GPP called 38.901. So I think many people know this under the names of TDL, CDL, urban micro, urban macro, rural macro cell. So these type of models. So TDL and CDL are actually simplified versions of UMI, UMA, and RMA. And we have implemented them all. And so these are the models that are used actually for 5G specification, and I would say the current gold standard in industry. And we felt, and what I had experienced in the past was that I was generating channel impulse responses for this model in another tool, created a huge data set that becomes quickly very large, and then import this into my TensorFlow environment to simulate things on top of it. And we felt that there was a huge gain of integrating this directly into Sionna so that you don't need to create data sets anymore and switch between tools. And so now with one line of code, you can actually go from Rayleigh fading to something 3GPP compliant, if you want, and make things more interesting.
Yeah, I think we were discussing this at one point as well, that this 3GPP compliance is important if you really are into pushing your ideas in standardization and things like this. So what are the sort of important sort of features that exist in these 3GPP models compared to if you just hack something simple together yourself? I remember we talked, for example, about something called spatial consistency once.
Oh yeah, okay. So So first of all, these are so-called stochastic geometry-based models. Essentially, when you place an antenna, a base station somewhere, a user somewhere, and then the channel impulse responses you can draw from these models do not correspond to any precise physical environment, but you try to mimic the stochastic behavior that has been obtained through measurements. And what's typically defined for a link is you have multiple so-called clusters from which you get reflections that arrive essentially at the same time at the receiver. And each of these clusters has an angle of departure and angle of arrival associated with it. And these are drawn randomly depending on the scenarios that you've selected. And then you also draw randomly the path delays that you get for these things. And then based on this, you essentially apply some of senoids to actually generate a time evolving channel impulse response. And then you can apply on top of this antenna patterns and also MIMO arrays where you just compute the corresponding phase offsets. And that's how you generate channel impulse responses from it. And so you have all of the practical effects. So you can say how fast does a user move, and this is really essentially determined then the Doppler spread. The antenna orientations are taken into account, leading to different correlation, directivity that impacts the rank of your channel and so on.
So you're sort of creating this kind of random environment with clusters of things, and then you move around in that one, and things are consistent.
You essentially say, I move, now I make tiny steps from this point where I was dropped and move for, a couple of milliseconds and generate essentially a snapshot, a sequence of channel impulse responses at this point. And then you essentially make another drop and you start again. And now I think, so with respect to, spatial consistency. So the problem you might have with these models is that when you drop two users almost at the same position, directly next to each other. By default, they can get angle of arrivals that are totally different. Meaning, although we are next to each other, I get a strong reflection from the right and the other user get one from the left, which does not make physically much sense.
Jakob, you're speaking of existing old models here, right?
That's the 3GPP. That's the 3GPP models by default.
The 3GPP, but that obviously has these weaknesses, right?
That's why I wanted to come to the point, so that there's now this so-called spatial consistency. This has been introduced into the 3GPP models. And what happens is then, to avoid that users that are located close to each other get these highly different channel responses, you correlate spatially all of the random variables that are used to generate channel impulse responses to kind of mimic as if you mimic a actual physical environment that you're simulating. But I think it's still very different from what you would get when you do actual channel measurements or when you do ray tracing.
So it seems like Sionna is really capable in terms of both like all the signal processing methods that are there and this 3GPP kind of models. Then I read your white paper where you write, despite the fact that Sionna supports 5G compliant channel codes and channel models, it does not try to by any means to be 5G compliant level simulators. Then I was wondering, is there something that is truly missing, or is this something just that the legal department needs you to add bad?
No. Okay. It's a good question. No, but so the reason we wrote this in the paper is the following. So Sionna is a tool for research and not a 5G simulator, right? We want to do something else and simulate 5G performance. And we do not want to be limited by anything that the standard describes. Now, the 5G channel models, I think, are great because they can be used to evaluate performance of any scheme you want to try. You can simulate a 4G system over this channel model, or something new you come up with, do OTFS over this channel model. And also the same holds for the channel codes. As Eric just said, I mean, these codes are great, right? And I think it's important to have them available for benchmarking simulations. So if you write a paper and say, hey, I evaluated with this 5G compliant channel code, I think it gives a lot of credibility to your results. And so that's why I think it's really important to have it available. However, I don't think that's a need for research to implement a 5G specific OFDM frame structure where you distinguish between control and data channels and have precise piloting schemes and so on. So I think for most research purposes, it's good enough to have, for example, a flexible OFDM frame structure where you have full control and freedom to do whatever you want. And I mean, being compliant with the standard makes things very complicated, and that's the opposite of what we want to achieve with Sionna.
Yeah, you mentioned 5G, but I had the impression that Sionna was thought of as a tool for 6G. Is that a right understanding, or how should we think about that? So, but then in that context, then what is really new here? What is 6G about it? In the sense that, I mean, what's new that could not have been or would not have been relevant like 5 years ago? Or even longer.
Yeah. So I mean, there are a couple of things that are new. I mean, obviously, machine learning is now well established, and I think it's very important for any link level simulator to provide a very nice interface to machine learning tools.
When you say interface, you really mean a native interface that facilitates the use of machine learning based methods at the receiver end, right? Like
and I mean, anywhere, wherever you want. I think wherever you want. So I think that's one part, and there are some people looking into AI native networks and trying to figure out if something could be actually even standardized using AI. So I think for this type of research, I think it is just important to have it there. But then I think there are quite a few new topics, such as integrated sensing and communications. You have these reconfigurable intelligent surfaces, terahertz communications, semantic communications. And for quite a few of them, for example, specifically the integrated sensing and communications and RIS topic, you can't read. The problem is that the channel models we have available don't really work well, because you really need to simulate a physical environment, right? If you want to do radar-based sensing, you can't use a stochastic channel model for it. And so I think, therefore, we need to resort increasingly to ray tracing to do 6G research. And I think the same holds for RIS. And that's one direction which we want to go with Sionna, but maybe you can talk later about the ray tracing aspects. And then there's also this idea of multimodal sensing. So there are people looking into, hey, I might have a camera that tries to help what a base station is doing. And then, for example, how now you need to generate a visual representation of a scene and get the channel impulse responses from it. And right now there is no tool that can do actually both. So you need to maybe use a rendering machine like Blender, and then use a ray trace and then combine the two. And I think with Sionna, we're really trying to bring all these functionalities together.
Yeah, so I can see, I mean, the machine learning aspect, that there's been a lot of new algorithmic developments over perhaps the last, say, 5 years in terms of like algorithms for receivers, or even trained end-to-end physical layer solutions, right, with modulation, coding, even MIMO and so forth. But I still feel like there's a need to separate a little bit here. On one hand, link level simulation for communications, and on the other hand, channel modeling, right, using more physics-based like techniques. You mentioned ray tracing, or I mean clusters, and then you move a little bit and see how the impulse response change and so forth. Because that's really a separate thing, I would argue. I mean, you could be interested in radar, not caring at all about link level simulations, right? And all you'd care about is like, what are the scattering centra, what does the speckle look like, and so forth. And but so in a way, it occurs to me that Sionna here does like both, or aims to, aspires to do both, right? Yeah.
No, that's true. That's true. So I think, my ultimate vision would be get rid of these channel models and do, if you can do it fast enough, do ray tracing in these kind of simulations, if you want to.
So obviously one of the good features here is the differentiability, and that you can sort of take an state-of-the-art algorithm or textbook algorithm and swap it out for some machine learning parts there. So you have been working for quite a while on machine learning improvement on the physical layer. How large improvement do you anticipate that it could be? Because on the one hand, you sort of, when you're teaching the fundamentals from textbooks, we try to say, this is an optimal code or this type of things, and then you go out there in reality and people say, we will improve things with machine learning. So what do you anticipate?
Right. Okay. Okay. So if you work on idealized models, like take the AWGN channel, where you already know that your solution is optimal, then machine learning will not be able to do any miracle. So in the best case, you are as good as your solution. But over the last years, I've now observed quite a few cases where there is a lot of room for improvement. So one example, is the random access channel. Those are the PRACH, for example, in 5G, where you need to detect a certain preamble, estimate carrier frequency and timing offset, and their fully learned solution can really achieve substantial gains here. So you might, in some scenarios, gain 10 dB in detection performance, for example. Or another area where fully learned solutions shine is when you do OFDM reception under very high Doppler spread scenarios. There you can actually, you observe really a couple of dB gains, and you can actually get these gains with almost no pilot demodulation reference signals if you want. So you can gain a couple of dBs here. Now the question is, this is nice. It's not a 10x improvement, and I don't think we probably see it on the physical layer.
No, but still a couple of dB is not bad, right? But I think the real question here is whether are these problems where there just aren't any good classical algorithms, or are these problems that have been maybe a little bit neglected because the academic community didn't want to or be too interested in working on them, or is it like fundamentally that a trained approach would do better? I'm not so certain. I appreciate the fact that these learned algorithms do work very well, but that in itself doesn't necessarily mean that one could not design classical algorithms that also would function rather well, in fact, and operate at a rather low complexity.
Yeah, so the thing is, let's take, for example, this PRACH detection. I don't think that there is any good algorithm that takes into account then you have a channel with when you essentially have a channel with memory a bit, because you always correlate. You have a sequence, you correlate it, you look for a peak, and you try, okay, that's the one. And this works well on an AWGN channel, but as soon as you have memory or you have strong CFO, the theory falls apart, and so we don't know what to do.
Maybe the thing is just here that these are problems that haven't attracted the attention that they really deserve, right? They aren't clean enough for many in academia to be willing to work on them, because you can't derive like provably optimum algorithm or closed form error probability trade-offs and so forth, and therefore nobody has really worked on them, and the solutions that are considered baseline and state of the art here are really simple and don't perform very well. And then it's not a huge surprise, that you by a trained algorithm can gain several dB then. So they sound to me to be more like problems that are being neglected. I've encountered this a lot myself in the past, that there are problems that are horribly important in wireless system design, but that nobody in academia wants to work on. Like control signaling might be the best example, how to optimize and detect the bits and so forth. And whereas you can find countless of papers on MIMO pre-coding using this MMSC or that MMSC and so forth. Why? Because the math is beautiful and you can prove in closed form some capacity and so forth, right? So there'll be like this notion of papers that address them. But that, of course, in itself doesn't mean, don't get me wrong here, I mean that a trained algorithm could not be the way to go even, because it could be perhaps that is just so efficient when you implement it on silicon. You could even leverage your GPUs and all this parallel framework and so forth. But I just wanted to state the point that these might also be to some extent problems that just haven't been carefully investigated using conventional techniques, and that's why the gains are so large, right?
That's a possibility. So that I would challenge the community to look at these orphaned problems. Come up with but there's actually another area, and I think that has received a lot of interest from academia, and I also think that there's no good solution. And that's it. I think some people call it massive unsourced random access. So we essentially have many devices that try to send very small data packets. And the problem is that from an information theoretic point of view, the classic approach where you would split such a short packet into a preamble and data is suboptimal, and would be better to do things essentially jointly. And there we have observed that you can generate essentially to learn to send self-contained radio bursts that just convey, let's say, a few bits of information much more efficiently than a traditional solution.
Yeah.
So I could imagine that for this type of area, massive IoT traffic, this could really also play a role.
Absolutely, but I think that might rather be a consequence of the fact that the approaches that have been considered in the literature, because this is still a bit of a niche topic or even a nascent emerging topic, right? These approaches are rather simplistic in their basic architecture, like as you said, sending a preamble and then sending data symbols, which is by no means optimum, right? And of course it's a hard nut to crack if you rather just pick I don't know, from a code book randomly where the preamble is like just an integrated part, and then you do optimum non-coherent maximum likelihood detection. That's a tough algorithmic problem where nobody really has a good solution, and where even solutions using classical methodology are likely to be somewhat ad hoc. And certainly, I mean, that sounds like a field where trained algorithms could have a role to play.
Yeah, and I wanted to make one last point
Yes.
with respect to I think there's another angle to it than just performance gains, which is the simplicity of implementation. So I mean, anyone who has ever implemented like a full OFDM receiver knows that it's very complicated, right? But you can actually train one based on neural network in a couple of hours. It's just and you get better or the same or even better performance. And now, so I'm not saying that this is what we should be doing.
Yeah,
but I think sorry, go ahead.
No, I have to rebut that. I mean, so when you say you train an OFDM receiver and so forth, does this mean training the entire thing? Because the way an OFDM receiver works is they have an analog front end, right? And then you sample with an ADC, and then you have a sampling rate converter, and you have a digital filter and so forth. And these are highly optimized pieces that go on silicon and essentially do the sampling rate conversion and the digital filtering simultaneously and all integrated, right? And then there's an FFT and so forth. So the question is, I mean, at what point in this chain do you really start and with this training like based approach, and where
good point.
You get your baseband samples in your Python script, right? That's not what you get actually from the antenna, or even close to what you get from the antenna. So
you just do import antenna. The thing is, I typically refer to either post FFT.
Yeah, I see.
Post FFT, something like this.
Yeah. So
but still,
like estimating channels, interpolating the channel response, and all that. Yeah,
computing LLRs and these kind of things, and just so easy. And for example, but I just made this as one example where I mean, I think we will resort in the future increasingly to machine learning just because it's much easier to train a model than to write an algorithm. I don't want to say let's get rid of theory and forget about understanding what's going on. It's just for some small problems, I think engineers will phase in the future, I mean, there is a simplicity that you have this tool that allows you to come up with a working solution very rapidly. Why not do it?
Yeah.
So
no, that I can concur, obviously. So I'm.
That's not how we should do research, but at least I just think from a practical point of view that makes a lot of sense to me.
Yeah. So I think another concern that one could have here is that you argued for the use of channel models that are based more on like physical models, right, and ray tracing in particular. When I speak to folks who do propagation, then I actually ask this question, so why don't you guys just do ray tracing? So you have a geometric model, here's the room, I have these walls and the table here and, you know, that shelf over there and so forth. Why don't you just do like ray tracing and then you simulate, so here's my antenna, it moves a little bit, every 10th wavelength or something, we just recompute the phases of all the reflected and scattered paths and so forth. And one thing I learned from that discussion that I had was that, well, it isn't as simple. I mean, for optics, it actually is. You can do extremely well as with a photorealistic rendering through ray tracing, right? But for RF, then there will be other factors that affect, for example, well, these are concrete walls. I'm sitting here now in the studio, and so there might be rebars integrated into the concrete, right? And the rebars, they aren't visible. We don't even know where they are, and they will serve to maybe scatter or, depending how densely how dense the rebars are, they might even just absorb the thing. But so even anything close to a physically realistic ray tracing model would require extremely precise knowledge of not only what we can see with a bare eye from photographs, but also what goes like behind the materials, the roughness of the walls and so forth. So I mean, I don't want to, I mean, I'm hardly like an expert myself on propagation modeling, but so I can only rely on what others and experts say. But the way I understood, at least, is that this is a tough call to actually do anything that comes close to physically realistic ray tracing. And that's the reason for why in propagation modeling that people tend to resort to these simple models with clusters. You throw out some scattering points and so on, right? Even, I mean, you don't even model reflections. If you have a wall, then you just, rather than modeling reflections at the wall, you put up, you model it through a number of scattering points, and that's it. Because I see a risk here, and the risk is that now your ray tracing model might be quite good, let's say, and then you train your algorithms and your you run your link simulation, and then you train algorithms that do well on the channel model that your ray tracing your ray tracer gives you. But isn't there a risk here that we like train algorithms that work well on some sort of quasi-physical models? When I go out in the field and actually get real impulse responses, they don't work as well. So that's a concern that I'd like to voice and maybe hear your views on also, Jakob.
Yeah. No, I mean, first of all, I agree that propagation modeling is very complicated. And I think, so, for example, diffraction, just to make it simple, is a huge problem in ray tracing. I think it hasn't really properly been solved. I mean, there's simplified approximations to it, but I think it's not yet done. So now where I kind of think where things might be going is the following direction. I think we probably will not succeed in creating, let's call it a digital twin of an environment. So, and we shouldn't probably not even, I don't see what would be the purpose of really trying to model exactly
and it might not even be physically possible, I tell you.
Yeah,
I mean, look at this globe here, right? I mean, it's from, I don't know, the 40s or 50s, I think, even. It's very old. And how do you know what's inside? Is it hollow? Is there some kind of like stuffed with, I don't know, some foam or paper or something? I don't know. The only way of finding out would be an X-ray the thing or take a knife and destroy it, which I don't want to do, right? So there's just no way you could model accurately propagation with that sort of objects. And this is a simple thing that sits on the shelf or the table here. But now if you think about it like a complete room, or even not to mention outdoors, right? How would you actually do this?
I think you can't. So, but where I think the value of ray tracing now for research would be, so even if it's just a simplified model, is that you actually get something that's let's call it physically consistent, meaning, as I said, you don't get these weird artifacts where
that
you
I can
suddenly
fully
get...
appreciate, and in a way it's a bit surprising. I mean, that the 3GPP models aren't better than that, right, or more realistic than that, because if you can get
I think it has never been. So that's coming back to the 6G discussion. I think until now nobody wanted to do something with these channel models that require it. So I wouldn't blame 3GPP for them. I think these models are great. So I would actually say now there are these new use cases where people want to do communications and sensing, or you suddenly start to control the environment and see things. And that's for the first time where we actually need this physically consistent modeling of the channel. And I think so now with ray tracing, this allows you to do this type of research. And now we actually need to see, okay, if I can now demonstrate in a ray traced environment that my algorithm shows gains, or that I can do something I couldn't do otherwise, then this justifies to do it in practice. And then we need to validate, does it actually work in practice?
Absolutely, point is well taken. I mean, that'll be like more convincing to most people probably rather than when you could demonstrate that it works with this correlated Rayleigh fading model or something, right? So I certainly appreciate that. I mean, my concern was only here that isn't there a risk that we like overtrain and design algorithms to just invert the simulation model rather than functioning in the true reality?
Yeah, I mean, so then now with respect to I think overfitting, or essentially to your simulator, I would say the thing is what you typically want to do when you do machine learning, right? You have a data set and you assume that it's kind of created by a data generating distribution. That's your environment, right? And in the best case, you learn perfectly the data generating distribution. Now, if it turns out to be our simulator that's flawed, then you have learned this. But if you have and now the thing is, what you then care about is how well will it do when I deploy it. And now, if you deploy your system somewhere where you have a different data generating distributions, then your model most likely is not going to work. So the only way to avoid this is by training on a better data set, training on real data. I think there's no way around training on real data anyway.
We're training on rich enough or diverse enough data sets, right? Because in the end, you'd like methods that work without too much of prior knowledge. There I strongly disagree. So I actually think I think where machine learning will really shine is when you can overfit to a specific scenario. So imagine you have a receiver that sits in a factory hall. It will only see this factory hall. So it doesn't need to work in a high, Doppler scenario or whatever. And so now if you can let your receiver algorithm overfit to this very kind of limited set of channel realizations we'll ever see, for example, that's probably something where you can gain a lot with respect to methods that would work anywhere at any time. Yeah. I think we don't disagree as much as the discussion maybe suggests here.
Yeah,
I think the point is rather, okay. I mean, the point is rather that, we'd like to build and develop basic technology that works without prior knowledge, right? But then obviously it's working, so performance could be improved by having it learn the characteristics of, let's say, a specific environment. So we build this wireless system. So here's the access point, here are the whatever terminals and so on, and then we just throw them out there in the field. The system just works, okay? But if we now put them up, so the access point in a factory, nothing changes there for like a year, right? In the topology, the machines don't move or anything. Then it's of course just a bonus if the system, if this access point can learn that, look, I seem to be in an environment that's just perfectly static, right? And there are these multipaths and so forth, and I can exploit that and minimize the latency and all the rest. So I think in that respect, we actually do agree.
Okay,
Jakob.
great. Okay.
Yeah.
Which is good, yeah.
Yeah, and I think what we are circling around a bit here is the fact that there are two sort of things that we learn when we design an ML-based algorithm. One is to sort of solve a problem in a general perspective, and that is where, maybe textbook solutions could be used as an alternative. And then the other thing is to sort of narrow down the applicability of the algorithm to a specific scenario, and then get this large gain from sort of overfitting for that situation. So one thing that I spent quite some time to sort of push is sort of this reproducibility in terms of research, and I think in the ML community, particularly maybe in like image processing, there's these huge data sets that everyone is evaluating their algorithms on, a large number of them. And then I've seen for a while in the wireless research journals, is sort of people always create their own simulation environment. So I propose an algorithm and I simulate and show that it's better than some baseline. And then someone else comes with a new algorithm and say it's better than mine. Fine, I take that. But then they evaluate it on their own system model, and you don't know if they cherry-picked something that where they were beating me, or if they were, it's always like that, it's just randomly or purposely. So I think one of the good use cases of Sionna, for example, is that now there is sort of much easier for people to always evaluate things using the same channel models. Provided that these channel models are applicable enough, so we are not sort of overfitting on and missing the bigger picture.
Yeah. No, I mean, I fully agree. I think our community has a massive problem with reproducibility, to be honest. And yeah, I mean, it's exactly as you said. So for most papers, there's no code or data sets available. If they're available, you might still not be able to run the code because they're missing dependencies. And so with respect to data sets, I think there's also this component of tools, right? In the machine learning community, you do not only have the data sets, but also most people publish their code using popular open source frameworks such as TensorFlow and PyTorch. And that also helps a lot because everyone's working with the same tool, and then someone has published the code, you can immediately use it and compare it with your research. And I think in our community, that such a tool is kind of missing, and that's to some extent the gap that Sionna tries to fill. Let's see if we are going to succeed or not. I fully agree. And also I think that we have, compared to the let's say the computer vision community, there are many people, maybe even thousands of people focusing on the same problem. Right? Say, let's may work on object detection or something like this. In our community, we don't have 1,000 people focusing on MIMO detection or this. So we have thousands of small problems, and you have a handful of people working on them. And so therefore, I don't think we will ever succeed in having these one huge data set with this one well-defined problem that everyone's working on to make progress. Rather, we have these many problems people are working on, but still it would tremendously help if we were using the same kind of tool or environment, the same channel models conditioned to evaluate our things. So I think maybe it's not the common data set, but maybe the common simulation environment that would help.
Yeah, it's really a commendable ambition, I think, to build that environment. And I think Emil's point was that, isn't there a risk if everyone is testing the algorithm on a specific ray-traced model from Jakob Hoydis? I don't know.
That's it, yeah.
Environment that we would just optimize it closely for that particular model, right? Rather than for a more diverse set of conditions we find in reality and so forth. But in any case,
coming back to this, so I think that's why it would be already great if we, these 3GPP models, for example, they are super rich, super versatile. I think they are also fairly realistic, and it would already be great if more people were using this, and that you can say, hey, I have simulated my MIMO detector on the CDL-A model, and then someone else does the same, and not coming up with a new correlation model. And so it's really a nightmare to compare things if it's not compared under the same conditions. So and then I also see, with respect to risk, so I think we need, two types of research, right? There's this one type of research that tried to make specific algorithmic improvements for a well-defined problem like MIMO detection. And for this, it's really crucial to get exact performance results that you can compare. But the other type of research, which I think is maybe even more important from in academia, is that of gaining fundamental insights and obtaining fundamental limits, scaling laws, and so on. And then for this type of research, reproducibility is maybe not much so an issue, because you have the mathematics, right? Everyone can prove that it's correct, and you can probably use simple and mathematically tractable models to obtain these fundamental insights. And so, I mean, as long as you have a good balance between these two types of research, I think we are good. So the only risk would be if now more and more people work on this niche problem and trying to gain 0.3 dB on this specific narrow scenario. That would probably not be so helpful.
Great. So I think we should start to wrap up the discussion about Sionna, because we wanted to ask just a few short questions about your previous work as well. But have people started using Sionna yet?
Yeah, I mean, there are quite a few groups that have started to use Sionna. I mean, we released it 2 months ago, and it's too early to have many papers appear using it. I think I just checked yesterday, and there's the first paper that uses one of the channel codes in Sionna as a benchmark. That's great. But I think more and more papers will follow this year.
And can people contribute to this open source project, or is it just like passive usage of it?
No, definitely. I mean, the whole point of an open source project is that people can contribute, and we need actually community contributions, because we are not experts on anything. And now there are various ways how you can contribute. So first of all, you can just use it and let us know about bugs, things that don't work. So you file a bug report in GitHub, or you can even propose a fix through a pull request. Then there's a discussion forum where you can just say, hey, I would like to do this. It would be great to have this feature enabled. Or if you say, hey, I'm working on a terahertz channel model, and is there a way to bring it into Sionna to make it available? We are happy to have a discussion and see how we can facilitate this. This is all possible. And then there's another way we think about letting the community contribute, is that we want people to make their Sionna-based research available to the community, for example, through Jupyter Notebooks. And we will have a dedicated section on our website that will just point to papers or the GitHub repositories with the corresponding code to advertise and tell people, hey, this has been implemented using Sionna. This is how you can access it. So it doesn't need to be really integrated into the Sionna core.
What is the license? Is this GPL or something else?
No, GPL would be dangerous. So it's Apache 2.0, and so that is essentially should allow anyone to use it, especially in industry, and you don't need to worry about infringing any patents. So that's why it's important.
Yeah, because they'll fork it in principle. I mean, so there could be forks appearing, right?
Of course.
Yeah. Yeah, great.
Yes.
So, Emil, how are we doing on time?
Yeah, I think we can have some just short things. See, I think you wanted to ask something about MIMO decoding.
Yes, MIMO decoding, Jakob. Is that is it already there? I mean, in Sionna, integrated into the say receiving end toolbox. I think you did some work. I mean, as you know, I mean, I also work on MIMO decoding, right? But it's like 10 years, I think, longer ago, and on what at the time was, I think, state of the art, no doubt. But you have more recently, I think, been looking at, and also perhaps before you came to NVIDIA, at machine learning inspired algorithms for MIMO decoding. So what would you say currently is like state of the art there? I mean, is it no longer the fixed complexity sphere decoder and my student developed, I think it was like probably 10 years ago now, this Sumis algorithm that beat every benchmark we could come across. But I suppose in the last 10 years, has machine learning really taken over to dominate the field, or could you comment on that?
Yeah. So I think sphere detection is very hard to beat.
Well, I mean, there's always a complexity performance trade-off. Exactly. That's the point, right? So then the question is, what is the hardware platform you're running on? And if you're running on the GPU farm or something, that's a different thing as compared to running on general purpose processor or an ASIC that's designed specifically for the detector. So, I mean, I appreciate it's a hard question to to answer or even to ask, because what does better mean here?
Yeah. So I think sphere detection is not yet used. I'm not sure if anyone has actually implemented practically in a commercial product, just because of complexity.
No, but I wouldn't even consider that state of the art. I mean, I think this fixed complexity, that's actually a misnomer, right? Fixed complexity sphere
decoding. You mean like K-best sphere detection or something like this? Or?
No, not really. I mean, there are these fixed complexity algorithms that aren't really sphere decoding, but maybe it takes the discussion too far to talk about these details now. But maybe let's summarize, like from a machine learning perspective, what would you say is the way to...
the problem there is the following. There has been in the last 5 years or so, I don't know, a few hundred papers on...
Oh, is that much even? I haven't followed.
Yeah, it's really huge. And the problem, and I looked into this for a very long time, and the problem is that almost all papers evaluate performance on the IID Rayleigh fading channel, and then they show, hey, we are close to maximum likelihood. And the problem is that that's very easy. But as soon as you try these algorithms on, for example, one of these 3GPP models, they totally fail. And some don't even converge anymore, not at all. And that reminded me a bit of what happened in the massive MIMO research community, where everyone was working on the IID Rayleigh fading model. We drew conclusions from it that turned out to be sometimes not so correct when you take a correlation into account. And now we have the same problem here, is that you go through this literature saying, wow, this is a great algorithm, they get performance, then you test it on an actual realistic channel model and it just doesn't work. And so I haven't seen a single machine learning based decoder that would work well on this 3GPP model. So there has been a paper a couple of months ago using self-attention that looked great, but I haven't looked into it in detail.
So what you are suggesting is that the way to go for MIMO detection is actually rather the classical algorithms then?
I'm not sure yet. I haven't given up yet, but until now I can't report on any. I'm not aware of any real success story.
Well, but that's actually good to know. I mean, I wouldn't be too surprised if the answer is that the classical algorithms are actually the way to go. The only reservation against that might be that if the precondition is that you are to implement this on a GPU, then there is a computational aspect where maybe the machine learning algorithms are just so much faster in some way.
Yeah, I mean, by the way, I'm not advocating for implementing the entire physical layer on the GPU. I mean, most base stations, they run on an ASIC.
I know, so that's why I'm saying there won't be a GPU, right?
So I'm...
Okay, I think we have covered most things. I had one last question for you, because I remember we wrote a few years ago this massive MIMO reality, what is next? 5 promising research directions for antenna arrays. And you were sort of assigned to write about something that has to do with AI machine learning. And then you brought up a topic that I haven't spent much time thinking about before, namely technical depth. So what is this and why is this a problem?
Yeah, okay. So now, I mean, this has a notion in software engineering, but I just focus on the part with respect to machine learning systems here. So when you think about a complex system that has many components, such as many signal processing blocks or like an entire 5G RAN setup. Now, when you start to replace certain components in such a system by machine learning models, you might create unintentional dependencies. And that's what technical debt refers to in this context. So for example, if you have one component that somehow influences the training data that is used for another component, then these two components are not independent anymore. Or imagine you have a chain of machine learning models where the changes in one model, impact the inputs to the next one. And this means if one of these model changes, all of the other models need to be retrained from scratch. And you totally lose these nice independent blocks that you can optimize and test independently of each other. So that's what meant by technical depth. And that's, I think, a problem that creeps into any system where you have multiple machine learning models operating together. And I think we have not seen this problem yet, as machine learning has not become like mainstream everywhere, but I think it's definitely going to happen.
Yeah, so if 6G networks are ML or AI native, then this will be one of the topics that we will be talking much more about in the future, I suppose.
I'm inclined to believe so, yeah.
Great. So, do you have any final words before we wrap this up?
Final words. I mean, I obviously I would like people to, the listeners to get started using Sionna. And I mean, we have put a lot of love into actually our website and the documentation. And if you want to give it a look, I mean, just browse through the website. There are quite a few tutorials that I actually think are also good for just to learn about digital communication. So I think it's actually also a cool tool to teach. So it's not just for research, so you can use it to teach. And these tutorials, you can run them directly in the browser. You don't need to install anything. And and I mean, otherwise, the only thing you need is a working Python environment. You do a pip install Sionna and you're ready to go.
That's amazing. So, I think we're all inspired to go and download Sionna and start
and
playing with it. So,
and we will put a link both to the white paper and to this website in the description of this episode. So with that, thank you very much. It has been a pleasure to have you here and talk about all of these things here and challenge your and get some of your deep knowledge around machine learning. So thank you very much.
Yeah, thanks for having me.
Yeah, thanks a lot, Jakob. It was really fun.
Bye-bye.
Bye.
Bye.